component of this addition will be AC times BF plus BD times AE, BDAE. Okay, and the second component will be BD times BF. Yes, and this is nothing but XY, the first term, and the second term is XZ. So yes, we are getting what we want. One more is left. If x is non-zero, then since x is a by b, so a should be non-zero, because we know that if a is 0, then x is also 0. X is the rational number 0, and we have x inverse. X is a by b. If it's non-zero, then its inverse is obtained by interchanging the components, which we have already seen in the definition of inverse. So by the definition of multiplication, this is AB by BA, which is nothing but 1 by 1, because AB times 1, which is AB, is equal to BA times 1, which is BA. That means AB is equal to BA, and that is because multiplication of integers is commutative, and this is our integer 1. So that's it. We wanted to prove all these things. Did we miss anything? We have proved that, let me just quickly see. Addition is commutative. Okay. Addition is associative, that we have proved in the text. X plus 0 is equal to x. Fine. X plus minus x is 0. Then multiplication is commutative. Multiplication is associative. We missed that one. No? Multiplication is associative. So let us write like this. Finally, because after associativity of multiplication, then only we have x times 1 equal to x, and then we have the distributive laws, and finally we have this extra condition which makes the system of rational numbers a field and the system of integers only a commutative ring. So we need to prove that multiplication is associative. This one is also very easy. This becomes a by b times c by d. So AC by BD times E by F, and this is equal to ACE by BDF. Now multiplication of integers is associative. We already have that fact, and we are going to use that here. A times CE divided by B times DF CE divided by DF. The first one is x and the second one is yz. So yes, now we are finally done with the proof. Then the fourth one. prove lemma. Okay, so we have to prove all the things. I mean, we have to complete all the proofs. That's just the exercise set. Only towards the end, I think we encounter one proper exercise which is not directly related to proving the results in the text. So this here, prove lemma 4 to 7. To 7. There is something else written. Note that as in proposition 2 to 13, you have to prove two different things. I need some ink. Two different things. Firstly, that at least one of A, B or C is true, and secondly, that at most one of them is true. Okay, now I remember what this is. It's the trichotomy of integers, rational numbers. That every rational number is exactly either positive or 0 or negative. So it's that one. At most one of A, B and C is true. Okay. Now we are going to, in proving this one, we are going to directly use the fact that we already have trichotomy of integers and rational numbers have been defined in terms of integers. So that's what we are going to use. So the solution goes like this. Let x be A by B. I think in the original lemma, the symbol x is already there. So here we don't need to say anything more. We are just assuming that x has the form A by B, where A and B are integers and B is non-zero. That also we don't have to mention. We just write like this. Then since x is also equal to minus a by minus b, because a times minus b is equal to b times minus a, or minus a times b. We can assume without loss of generality that b is actually positive. See, a and b are integers. The only restriction is that b is non-zero. It can be negative also, but if it is negative, instead of this representation we will use this representation. So in any case, the second component can always be made, can always be chosen in such that it is a positive integer. We do this to make the sign of x, that is whether it is positive or negative, dependent only on the sign of the first component. To do that one, we use this. Okay. Now by the trichotomy of integers, exactly one of the following three statements is true. A is equal to 0. A is a positive integer and the third statement is a is a negative integer. Okay, we already have the fact that exactly one of these three statements is true, whatever a may be. So by what was the definition of positivity? Definition 426. Okay, so definition 426 implies that correspondingly exactly one of the following three statements is true. Whenever a is 0, the rational number is also 0, and conversely. Okay, if the rational number is 0, a must be equal to 0, and x is a positive rational number. For that, there must be integers a and b such that a and b are both positive. You can go to the I forgot to write definition. You can go to definition 4.2.6 and see what positivity of a rational number means. So that tells us that x is positive if and only if there exist positive integers a and b such that x is equal to a by b. x is a positive rational number, and the last one is x is a negative rational number. That's it. Okay, then next one, the fifth one, prove proposition 4 to 9. So it's that one which gives us the basic properties of order. Okay, so it had several parts. Part A. Part A is the one which gives us trichotomy of order. That is, if x and y are two rational numbers, then exactly one of these three statements is true. Namely, either x is, the statements are, the first one of them is x is less than y. The second one says y is less than x. And the third one says x is equal to y. Exactly one of them has to be true. And that directly follows from this one. This trichotomy of rational numbers and definition of order. So we are going to simply write it like this. It follows from this trichotomy of rational numbers, lemma 4 to 7, and the definition of order, definition 4 to 8. That's just it. Then part B. In part B, we have to show that order is anti-symmetry. Okay, so we have x less than or equal to y and y less than or equal to x. This implies, according to definition 4 to 8, this means either x is less than y or x is equal to y. So x is less than y or x is equal to y, and at the same time this one implies y is less than x or y is equal to x. Antisymmetry asserts that x is equal to y. To the contrary, let us suppose that x is not equal to y. Suppose x is not equal to y. That means in both of these statements, this part is not true. Now, since both the statements are disjunctions, that is or, so if this is not true, then the other one must be true, because the statement itself is true in both the cases. Then we must have x less than y and y less than x. Now we apply the definition of order itself. So this one says that y minus x is a positive rational number, and this one says that x minus y is a positive rational number. So y minus x comma x minus y are both positive rational numbers. These are both positive rational numbers. Now if you have two positive rational numbers, although we have not proved it anywhere, but you just think of it, you have two positive rational numbers, then for them we will have positive integers. For the first one we will have a and b such that the rational number looks like this, and for the second one we will have c by d. Now if you add them up according to the definition of addition, this is ad plus bc by bd. Since a, b, c, d, these are all positive integers, ad plus bc is a positive integer and so is bd. That means the sum itself, again by definition 4 to 8, a positive rational numbers. That is, if we add two positive rational numbers, we again get a positive rational number, and we are going to use that here. So their sum y minus x plus x minus y, which is 0, is also a positive rational number. That's what we are concluding. However, 0 is equal to 0, so 0 cannot simultaneously be positive because that would contradict trichotomy of rationals, and that is our contradiction. But this contradicts lemma 4 to 7. So that means our supposition is wrong. That is, we must have x equal to 5, and this proves anti-symmetry. Part C is transitivity. So here we have the exact thing is given in the statement. No, so I should not write something which is not there. X is less than y and y is less than z. Then by definition of order, y minus x and z minus y are positive rational numbers. So same like the above one. So their sum plus z minus y, which is nothing but z minus x, is also a positive rational number. This implies, by definition 4 to 8 again, z minus x is positive, so x is less than z, proving that order relation is transitive. I think two more are left. No? Addition preserves order and positive multiplication preserves order. Then part D, addition preserves order. We have x less than y, then y minus x is a positive rational number. That is, now y minus x can also be written like this: y plus z minus x plus z is a positive rational number. So again, by definition 4 to 8, x plus z is less than y plus z. So this shows that addition preserves order. Finally, positive multiplication preserves order. We have this, and z is a positive rational number. But the ink is already gone. So here we will get two positive rational numbers again. So y minus x and z are both positive rational numbers. So their product will also be a positive rational number. That is in fact even easier to see that it is positive than sum. This implies that their product, which is y minus x times z, and that turns out to be yz minus xz, using all the laws of algebra for rational numbers which we now have, is also a positive rational number. Hence xz is less than yz. So that's it. This proves that positive multiplication preserves order, and this completes the proof of this. What was this? Proposition 4 to 9. And there is one more exercise which explores the condition of, which explores the condition what happens when z is negative instead of positive. Then the inequality is reversed. Show that if x, y, z are rational numbers, such that x is less than y and z is negative then yz will be less than xz. The inequality gets reversed, or in other words, xz will be greater than yz. We have x less than y and a negative rational number z. Then y minus x and minus z are both positive rational numbers. Y minus x is a positive rational number that is coming from here, and negativity of z implies minus z is positive. We are not using any result to conclude that minus z is positive. Notice that it is coming directly from definition 4 to 8. So their product y minus x times minus z, which is equal to, you can apply the laws of algebra, and this will give us xz minus yz is also a positive rational number. Hence yz is less than xz. That's what we wanted to show. So this completes the current set of exercises. From the next video we will look at the section 4.3, where we will see more things about, although the system of rational numbers has been built completely and we have proved all the basic things that we need to prove, but there are more things in this system that we need to know about. So we will look at them in the next section.